We're going to conclude with a discussion of linear dynamical systems. This is sections 9.1 to 9.3 in the book. Because time is short, I'm going to skip around in these sections a bit and omit some material. So rather than proceeding sequentially, I'll just group all three of these sections together. This is a very important application of linear algebra, and it really brings together a lot of the ideas that we've been talking about throughout the semester. So I'd like to cover the basics of this stuff. So let's get going. So the basic idea is the following. You have a differential equation of the following form. df dt is some constant times f, where f is a function of t here. So this is a differential equation. It says, we've talked about this before, where I want to specify f by this equation. I'm looking for a function whose derivative is a constant times itself. And we've seen that the answer to this is f of t is some constant capital C e to the c times t. And, well, that's not really a linear algebra problem, but we're going to make a linear algebra problem as follows. Suppose I had a pair of functions, f1, f2, and I had an equation, a system of equations. I suppose I asked that df1 dt was equal to a f1 plus b f2, and df2 dt is equal to c f1 plus d f2. So it's a pair of equations, and I'm supposed to be solving this to find two functions, f1 and f2, which satisfy this, and they're obviously linked in that f1 and f2 both occur in each of these two equations, and so you can't just solve them separately in most cases. And, well, it's sort of obvious that somehow what's playing a role here is this matrix A, B, C, D. I can rewrite this as a vector equation as follows. Define the function f of t is the pair of functions f1 of t, f2 of t. And then this pair of equations simply becomes df dt is equal to this matrix A, B, C, D applied to f. All right, so that this is just shorthand for this here, because df dt, well, that's shorthand for df1 dt, df2 dt, and df1 is given by this, and df2 is given by that. If you write this out with f1 and f2, you get exactly this pair of equations. And this is the general example of a first order linear homogeneous differential equation in two variables. All right, so that's a lot of words, and in some sense I don't really care that much, but let's go over what all of these words mean. So, well, it's a differential equation because it's a differential equation. I'm specifying a function by its differential. It's first order. That means that the highest order derivative which appears is a first order derivative. What you have here is df dt, which is order 1. You don't have the second derivative, dt squared, which would be order 2. So first order is saying that there's just a first derivative. Linear says that it's given by this matrix, well, linear and homogeneous together say that the equation is given by this matrix. And the two variables, of course, is that I have f1 and f2. Okay, so let me just write down the n variable version of this. So the generalization would be an equation like this, where f of t is f1 of t down to fn of t, and A is an n by n matrix. Well, that's the general n-variable first-order linear differential equation. And we're going to focus on the case n is equal to 2. All of the interesting phenomena already happens there. So we're going to talk quite a bit about that. So let's do an example. I've been saying for a couple of days now that diagonal matrices are really nice. So let's look at a diagonal example. So we're taking n is equal to 2, and suppose A I took to be a diagonal matrix lambda 1, lambda 2, where lambda 1 and lambda 2 are any numbers. So this is the equation f1, df1 dt df2 dt is equal to lambda 1, 0, 0, lambda 2, f1, f2. And that says that it's a pair of equations, which is to say df1 by dt. The first coordinate here is equal to lambda f1, and df2 dt is equal to, that's a lambda 1, and this is lambda 2. And so these are unlinked. There's no... This is all about f1, and this is all about f2. There's no cross-pollination here. So this is essentially really just a one-variable problem. You know that f1 is some constant c1 e to the lambda 1t, and f2 is equal to c2 e to the lambda 2t. So when you have a diagonal matrix, this is extremely easy. And now the whole point is if you have a general matrix, do eigenvalues and eigenvectors, and see how it resembles, relate it to the diagonal case. That's kind of the whole ball game here, is that if you had a general 2x2 matrix, if it's not diagonal, well, eigenvalues and eigenvectors are telling you, for example, that you might be able to diagonalize it, in which case you can relate it directly to this. And if it's not diagonalizable, well, that requires a little bit of extra discussion. So let's do an example. Suppose A was the matrix 4 minus 2, 1, 1. And so I'm looking at f df dt is equal to A times f. And f, of course, is this pair, f1, f2. So never mind all of that. Let's look at this matrix and calculate its eigenvectors and eigenvalues. Well, the characteristic polynomial is 4 minus lambda times 1 minus lambda plus 2, which is to say lambda squared minus 5 lambda plus 4 plus 2 is equal to plus 6, which is to say lambda minus 2 times lambda minus 3. Okay, so when lambda is equal to 2, A minus 2i is equal to 2 minus 2, 1 minus 1. So V sub 2 is equal to 1, 1. And when lambda's equal to 3, then what you get here is 1 minus 2, 1 minus 2, and V3 is equal to 2, 1. So these are the two eigenvectors, and the 2 and the 3 indicate the corresponding eigenvalues. So what this says in this example, the eigenvalues are distinct. So this system is diagonalizable. If I use the basis V1, V2, then the matrix would simply be the matrix 2, 3. And then it would be very easy to solve. Well, that's because I chose this basis. I want to be able to solve it in the original basis. And, well, if you unwind that, you see the following. Well, the point is that V2 is playing the role of 1, 0. And 2, 1 is playing the role of 0, 1. This is the usual basis, and this is the new basis. And what happens is the following. Consider the function f of t is equal to e to the 2 times t times v2. Okay. So this v2 is a constant vector, 1, 1, and this is this exponential times that, or in other words, this says that f1, f2 is equal to e to the 2t, e to the 2t, or to be completely pedantic about it, f1 is e to the 2t, and f2 is e to the 2t. And I claim that this satisfies the differential equation. Let's check that this is true. So, on the one hand, what is df dt? What is df dt is equal to, it's the derivative of e to the 2t v2. And v2 is just a constant, and the derivative of e to the 2t is 2e to the 2t times v2. And on the other hand, what is a times f? Well, a times f is a applied to e to the 2t v2. And e to the 2t is a number. It depends on t, but for any fixed t, it's a number. And a is just some 2 by 2 matrix. There's no derivatives or anything, and so this is just a constant. It just pulls out. This is e to the 2t times a applied to v2. This is just a constant for any given value of t. And a applied to v2 is 2 v2. And, of course, these two things are equal. Okay. Now, obviously, I can do the same thing with the other eigenvalue. I could have taken f of t is equal to e to the 3t v3. And that's also a solution. And notice that, what is v3? V3 was a 3 eigenvector. I took v3 to be 2, 1. But any 3 eigenvector would work. Or I could have taken any C3 times that. For C3 is any constant. So in other words, instead of writing V3 here, I could have multiplied it by any constant. And that would still be a solution. Because all I'm doing is I'm replacing the eigenvector V3 with a new eigenvector, which is C3 V3. And, well, a basic fact is that you can add these also. So f of t is equal to c2 e to the 2t v2. So I did the same thing here. I took e to the 2t v2 and allowed myself a constant out front. And you can add c3 e to the 3t v3. And the fact is that this is the general solution to the differential equation, is the general solution. And where C2 and C3 are allowed to be any scalars. So let's check this directly. I claim that if f is of this form, then f prime is equal to AF. So what do I have to check? Well, f prime is the derivative with respect to t of f, which is c2 e to the 2t v2 plus c3 e to the 3t v3. And now the crucial point is that the derivative of a sum is the sum of the derivatives, and the derivative of a constant, the constant pulls out. This is c2 times the derivative of e to the 2t v2 plus c3 times the derivative of e to the 3t v3. And what we saw is that, well, this is just 2c2 e to the 2t v2, and this is 3c3 e to the 3t v3. So that's the left-hand side, f prime. And now let's compute the right-hand side. AF is equal to, it was the matrix 4 minus 2, 1, 1 applied to F, and that is to say it's applied to c2 e to the 2t v2 plus c3 e to the 3t v3. And what is that? Well, again, this operation is linear. So a matrix applied to a sum is the sum of the matrices and so on. So this is simply c2 e to the 2t 4 minus 2, 1, 1 v2 plus c3 e to the 3t times this matrix applied to v3. And, well, this is an eigenvector, so this is 2c2 e to the 2t v2, and then this is a 3 eigenvector plus 3c3 e to the 3t v3. And that's this side. And are these equal? What do we need to check? This is equal to this. So it's true. Okay. So I basically just proved the following theorem. I did it in an example, but everything I said goes through. Suppose I had the equation f prime is equal to a times f. And here I'm writing f prime as shorthand for df dt. And let's say we're in the A is a 2 by 2 matrix. And suppose A has eigenvectors, eigenvalues and eigenvectors lambda 1, v1, lambda 2, v2, where lambda 1, where v1 and v2 are linearly independent. v1 and v2 are linearly independent. So that is to say A is diagonalizable. Then the general solution to this equation f is equal to c e1 e to the lambda 1 t v1 plus C2 e to the lambda 2t v2. And this is for C1 and C2, any constants. Okay? So the fact that that I've written down here is a solution, I basically just did. You just plug it in and check. The fact that every solution is of this form, this gives all solutions are of this form. That requires a little bit of extra work, but never mind, that's true. So that's the general solution. And of course, because we have C1 and C2, this is a two-dimensional vector space. This is a two-dimensional vector space of functions with the basis e to the lambda 1t v1 and e to the lambda 2t v2. These two functions. And these are vector-valued functions. These are functions from R to R2. You take the number t to the this constant e to the lambda 1t times this vector. Okay. Okay, so let's try and draw a picture of what's going on here. What do I mean by that? Well, I have this function f, and as I just mentioned, you should think of f as being a function from R to R2, where you take a real number t, and you get this f of t is a vector in R2, and as you vary t, you vary f of t, so you're getting some sort of curve. Now, which curve you're getting depends on C1 and C2. So, depends on C1 and C2. So, you get some sort of family of curves. And let's look at this particular example and see if we can figure out what we get. Obviously, it depends on V1 and V2, and not to mention lambda 1 and lambda 2. So, let's draw a picture. Suppose V1 was here, say, and V2 was over here. And for the sake of discussion, it depends on what lambda 1 and lambda 2 are. So let's do an example where lambda 1 is positive and lambda 2 is negative. Okay, so what do these curves look like? Well, as a sort of very simple example, if C1 was equal to 1 and C2 was equal to 0, you'd just have the function e to the lambda 1 v1. So that is to say f of t is equal to e to the lambda 1t, e to the lambda 1t. Of course, I'm missing a t up here. E to the lambda 1t v1. And so when t is equal to 0, you're getting v1, and lambda 1 is positive, and so you're getting this straight line out here going to infinity. This is f. Okay? And similarly, if c2 is equal to 1, but c1 is equal to 0, you're getting e to the lambda 2t v2. And since lambda 2 is less than 0, e to the lambda 2t is going to 0 as t goes to infinity. So this is t goes to infinity along this curve is going out to infinity. But here it's going the other way as t goes to infinity. This solution is going to 0. Okay, well, what if I took something like C1 and C2 were both equal to 1? What would that look like? Well, when t is equal to 0, you'd be getting you'd be just getting v1 plus v2. So that would be out here. And now, what happens as t goes to infinity? Well, as t goes to infinity, since lambda 1 is positive, this is going to infinity, whereas this term is going to 0. And so, if you think about it, what that says is that you can ignore this term, and you're getting closer and closer to this solution. And what happens is you get a curve which goes like this. And on the other hand, as t goes to minus infinity, it's the opposite. I didn't draw this very well, but in the other direction, it goes asymptotically this way, and there's not supposed to be a kink there. So the general curve looks something like this, with the arrow pointing this way. So as t goes to infinity, it gets closer and closer to this straight line. As t goes to minus infinity, it's going the other way. And you actually get a whole family of curves. Let me draw these lines like this. You get another whole family of curves over here, and a family over here, and a family over here. And if you put arrows like this, indicating that the eigenvalues along this direction are positive and this direction are negative, you can put arrows on these corresponding curves that sort of go in the same direction. So that is the collection of solutions. So as C1 and C2 vary, you're getting these various curves. And the solution that you're looking for, one way to think of it is it depends on an initial condition. If your initial condition was this point here, then the solution which goes through that point would be this curve. Okay, I think that's a good place to stop. I will talk more about that in class and in the next video.